Welcome back. Today we're cracking open one of the absolute biggest, most stubbornly persistent mysteries in modern physics. We're talking about a fundamental clash between the two greatest scientific theories of the 20th century. So grab your notebooks because we're going to look at how a brilliant team of physicists is literally trying to catch time acting weird inside a quantum trap. Okay, let's dive into this. What actually happens when the rigid, predictable ticking of Einstein's clock falls headfirst into the blurry, chaotic world of quantum mechanics? That question right there is the absolute heart of this cosmic clash. You see, on one hand, we've got Einstein's strict rules of relativity, where time is this physical fabric that bends and stretches. On the other hand, we have the fuzzy, totally unpredictable world of quantum mechanics, where reality is, just a cloud of probabilities. And for decades, these two theories have flat out refused to speak the same language, especially when it comes to time. But that is finally changing. We are treating this paper like the massive breaking news story it absolutely is. It's titled Quantum Signatures of Proper Time in Optical Ion Clocks. It's authored by Gabriel Cerci, Joshua Fu, and their incredible team, and it was just published in Physical Review Letters. Now, this isn't just another dense math paper, okay? It's a literal blueprint for a Nobel-worthy breakthrough. They've figured out how we can use state-of-the-art atomic clocks to finally actually observe time behaving by quantum rules. It's the first real bridge over a century-old gap between quantum mechanics and gravity, and that is a real game changer. Section 1. The classical time problem. So think of these researchers as detectives trying to solve a century-old physics cold case. Here's the crux of the problem. General relativity treats time dynamically, right? Time bends smoothly depending on how fast you're moving or how strong gravity is. If you run really fast, your watch ticks slower. But quantum mechanics, it treats time as a fixed, kind of boring background parameter, just a ticking metronome that never changes, even while the particles themselves exist in multiple places at once. The two ideas just don't play nice together.
And here's the thing. Up until now, our tests of time dilation have been purely classical. Picture this. Back in 1972, physicists Hafele and Keating actually flew atomic clocks around the world on commercial airplanes. No way, right? But they proved that the clocks on the planes ticked slightly slower than the ones on the ground. It was absolutely amazing, but they were still only measuring a fixed, classical time parameter. We hadn't yet seen the quantum blurriness of time itself.
Section 2. Catching time in a trap. And this brilliantly illustrates how the researchers plan to force time to show its quantum nature. They modeled a single atomic clock trapped inside a sort of bowl-shaped electromagnetic field. At first, the classical clock is just swinging back and forth, like a pendulum. But as we move further along, the clock enters a blurry quantum state. It isn't just in one place anymore. It's physically smeared out. And because it's smeared out in space, it's actually moving at multiple speeds simultaneously, meaning it is experiencing multiple different flows of time all at once. Which brings us to their first truly mind-bending discovery, the vacuum-induced second-order Doppler shift, or VSODS. Imagine you cool this trapped atom down to absolute zero. It's the lowest possible energy state. It's perfectly still. Well, actually scratch that. It's supposed to be perfectly still, but it still experiences time dilation. Why? Because of the quantum jitters of empty space. The atom's position is fundamentally fuzzy, so its momentum is fuzzy, meaning it technically has motion, which dilates its time. The quantum vacuum itself is changing how the clock ticks. Now, you might be wondering, how do you detect a vacuum jitter that tiny? Well, the physicists propose a clever trick, using what's called a squeezed state. Think of it like squeezing a long balloon. If you squeeze the middle really tight, the ends bulge out wildly. By forcing the atom's quantum blurriness to be super precise in its position, they make its momentum, its speed, wildly uncertain. And this massively amplifies those quantum time dilation effects, pulling them right out of the realm of pure math and into something we can actually measure in a lab. Section 3. A new quantum reality. Now, what's really interesting about this is what happens when we squeeze this clock and just let it tick. There's this incredible interplay happening. You've got the physical, spatial motion of the clock on one hand and the internal ticking of the clock on the other. As the clock evolves, its physical motion and its internal ticking become permanently, inextricably tangled. The time the clock experiences depends on its fuzzy quantum motion, and its fuzzy quantum motion is altered by the ticking of the clock. They call this time dilation-induced entanglement. And that leads to the single most important insight from the entire paper. This entanglement can actually become observable. Now, to be clear, this paper is a theoretical model. They haven't flipped the switch on the physical experiment just yet. It's a roadmap. But we can be highly confident here because the technology to do this, specifically these highly controlled aluminum ion clocks, literally exist right now in labs today. We finally have the physical path drawn out to observe the fabric of time tangling with quantum motion. So let's quickly summarize the three distinct ways time shifts in this trap. You've got the standard shift caused by classical heat and motion. Then, you've got that vacuum shift caused by the quantum jitters at absolute zero. But the real star of the show is the squeezed state shift. When the clock's motion and time get entangled, the internal ticking of the clock actually gets fuzzy to our instruments. It causes what physicists call a loss of visibility. And that loss of visibility? That is the smoking gun. It's direct proof that we are seeing quantum weirdness bleeding into the flow of time.
So, the crucial point is how this fundamentally shifts our whole scientific landscape. By proving we can measure these effects, this paper literally paves the way to testing quantum gravity in a lab setting. It's going to force us to rewrite our models of relativity to finally include that quantum fuzziness. And on a practical level, this could lead to the creation of ultra-precise quantum sensors that could do things like map the Earth's interior, detect dark matter, or even help us navigate deep space without needing GPS.
We have spent a century thinking of time as the smooth, invisible river. But this research shows us that at the absolute deepest levels of reality, that river is churning with quantum static. If the fabric of time itself is fundamentally blurry and tangled up with motion, what does that mean for the reality you and I experience every single second? It is a profoundly wild thought to leave you with today. Thank you so much for joining me on this explainer, and keep questioning the universe around you.